some point in the near future, we'll also be posting things like Beamer slides, so that you can see them. But the videos are online already, and the talks from today will be posted online before the now for Rob's third talk.
Oh, well, thank you. So in particular, to follow up on what Matt was just saying, I noticed during my first two talks there were people frantically trying to write down every word on my crazy slides. So you don't need to do that. They're going to be posted, if they're not already, very shortly. Okay, so let me just start off by going back to some examples. So these are this example appeared in my first talk. I'm sure it's long since forgotten, but now like revisited from the Berkovich standpoint. So take a quadratic polynomial. Joe was just saying you can change everything to any quadratic polynomial to the form z squared plus c. Well, you can do that in characteristic 0, but you need to complete the square. So if you're in characteristic 2, you can't quite do that. But if you're willing to possibly go to a quadratic extension, and I'm working on over an algebraically closed field, so I don't care, you can get any quadratic to look like this, even if the characteristic is 2. Anyhow, so any quadratic polynomial looks like that. And we get this dichotomy between what happens if absolute value is less than or equal to 1 or bigger than 1. All right, well, if it's less than or equal to 1, I commented last time the closed unit disk maps into itself. So now in the language of Berkovich space, then that is saying that, in fact, the Gauss point maps to itself. The Gauss point being the point in Berkovich space corresponding to the closed unit disk. And indeed, the reduction of the map there is just, well, take this guy and reduce the coefficients mod the maximal ideal. Because absolute value of A is less than 1, you can do less than or equal to 1, you can do that. And this map here, defined over the residue field now, has degree 2. So that's good reduction, or in particular, it's non-constant reduction. So what all right, that's good reduction because the degree did not drop. And indeed, what happens in that case, I'm asking you to accept something on faith as usual again, but it turns out whenever you have good reduction, whenever you have the case of the Gauss point maps to itself, so in other words, the map is the reduced map is non-constant. But not only that, if the reduced map actually has the same degree as the original map, that's what good reduction is. In that case, any given residue class maps to the residue class corresponding to the reduced map at that residue class. So let me say what I mean by this. So in other words, what's going on is, so let's say here's the Gauss point, and you have all these various things coming off in these various branches. So if you have some type 1 point x down here, and you want to know what phi of x is, well, this x is on this whole region here is the residue class of x. I mean, that's the modulo the maximal ideal. That entire open branch extending from the Gauss point is the residue class of x. Now, phi bar will take this, so this is an element of the residue field here. Phi bar will take that to some other point in P1 of little k, which say corresponds to corresponding to this branch, let's say. So this is the branch phi bar of x bar, so that's also in P1 of k. Well, the point is x, phi of x must land somewhere inside that branch. That's what I'm saying here. And that only happens, that can only be guaranteed anyhow in the case of good reduction, but it is true. So that one entire branch here lands entirely inside this entire branch here. And using the fact that that's true for every residue class, it's not too hard to show that every single residue class, every single open branch extending off the Gauss point is contained in the Fatou set. Its dynamics is very controlled. Nothing crazy happens. However, the Gauss point itself is in the Julia set. It's a repelling fixed point, so automatically it's in the Julia set. It's repelling because its degree here was at least 2. So the Julia set now consists of exactly one point, the Gauss point, and the Fatou set, this is the Berkovich Fatou set, and Berkovich Julia set is everything else. Okay, on the other hand, if you don't have good reduction for this map, so if the absolute value of A is bigger than 1, well, you can't do this again. You can't take 5 mod the maximal ideal because A is bigger than 1. You can't define what A bar means, its reduction. But it turns out by the same kind of computation I whipped before your eyes in about 10 seconds in the first lecture, that the Berkovich-Julia set coincides with the classical Julia set. So it's this crazy Cantor set. And that was the argument where I said you start with this one disk and you show that the preimage of that disk is 2 disks contained in it, and the preimage of those 2 disks is 4 disks contained in those, and the preimage of that is 8 disks contained in that. And all the radii go to 0, and the Julia set is the thing in the intersection, which is this Cantor set. Incidentally, in answer to the question that was asked, you can rig that up so that entire Cantor set is actually contained in QP, say, for example, if you're working over CP. So you can get the entire Julia set, including all of the pre-periodic points, to be contained in QP, for example, using that trick. And the Fatou set, even the Berkovich Fatou set, is everything else, because every other point in Berkovich space, not just the type 1 points, but all of them that weren't actually these type 1 points that were in the Julia set, all the other Berkovich points eventually get sucked outside of these disks and get sucked off to infinity. Okay. Now this slide is titled Revisiting the Cubic Polynomial Example, but I had to cut my first talk short, so this is visiting the cubic polynomial example for the first time. So the idea is here with this map, the key thing is the absolute value of A is less than 1. And if you look at the reduction of this map, when you reduce it mod the maximal ideal, the A term, the cube term dies. And now, so this is not good reduction because the degree actually dropped. So it's not a map of good reduction. However, it's still non-constant reduction because it didn't drop all the way to 0. And in fact, because the degree is 2 and 2 is bigger than 1, that means the Gauss point is a repelling fixed point. Not just fixed, but in fact repelling. So what's going on here is, if this is the closed unit disk, it turns out that this disk maps into itself 2 to 1. In particular, everything in there is Fatou, because if you look at the successive iterates of that disk, they're all contained in the disk, and the things are controlled. They don't go shooting off to infinity. So everything here is contained in the Fatou set. Now it turns out you can just check that there is a point somewhere out here, let's call it alpha, where the absolute value of alpha is equal to 1 over the absolute value of A. So in particular, it's bigger than 1. So well outside the closed unit disk. And it's a repelling fixed point. Again, this is a routine calculation to check that. Now, what's going to happen then, let's see, what else do I say on this slide? So first of all, yeah, as I said a second ago, now in the Berkovich language, so before we had Berkovich language, we just said, oh, the closed unit disk maps into itself 2 to 1. But now we're actually saying that in Berkovich space, what's going on is that you have the Gauss point, and you have all these things extending down from it. Well, so all those little branches I just drew map to each other. The Gauss point itself maps to itself. So everything down here is Fatou, and the one boundary point of that region I just shaded is the Gauss point. That point is Julia. So it's sort of at the end, the boundary point of that component, so to speak. No, it's not really a component. I shouldn't call it. So what happens? Oh, still talking about what's going on with the Gauss point. Of all these infinitely many branches at the bottom, again, for the same reason as with the quadratic case, each residue class maps to another residue class. It's only sort of the residue class extending off to infinity that is bad. The residue classes that extend, so let me see what I'm saying. So there's this residue class up here that extends to infinity, and this is bad. Bad stuff happens when you try. If you take the image, that corresponds to some open P1 disk, the complement of the closed unit disk. The image of that open P1 disk, the complement of the closed unit disk, the image of that is the entire Berkovich sphere. It's everything, it turns out. This can be checked. But all of the other branches off the Gauss point are fine. If you take the image of one of those, you get another branch. And so they all sort of behave nicely. And because this is a polynomial, none of the branches none of the lower branches get mapped to the upper branch. Because polynomials don't send anything to infinity besides infinity. So the thing is, everything downstairs is well behaved. So that's why they're all, from that point of view, they're all contained in the Fatou set. But this point, but then, like I said, you have this point alpha, And alpha, by the way, on the Berkovich diagram, is extending off of some side branch of the branch heading up to infinity, okay, because it's outside of the closed unit disk. So there's badness happening outside of the closed unit disk. And there's, in fact, going to be lots of Julia sets scattered up there. So here are some other points that are in the Julia set. Any preimage of a point in the Julia set is also in the Julia set. Alpha is a repelling fix, so it's in the Julia set. So there's also some point you can check, let's call it beta 1, which has absolute value square root of that of alpha. That's sitting around out here. And then there's a point a little closer, smaller absolute value, beta 2, whose absolute value is alpha to the 1/4. And then there's another point, beta 3, whose absolute value is alpha to the 1/8, and another one, beta, and in general, a beta n, if you want to continue this as far back as you want, whose absolute value is alpha to the 1/2 to the n. But that's still bigger than 1, of course. And all these betas that I just drew are all in the Julia set because they all eventually map to alpha, which is in the Julia set. And if you notice, this sequence of betas is a non-Cauchy sequence because they all have different absolute values that are bigger than 1. So if you look at the absolute value of beta n minus beta m, let's say where n is bigger than m here, that's just dead on equal to the absolute value of beta m because they have different absolute values. In the non-Archimedean world, if you take the sum or difference of two things that have different absolute value, that sum or difference is dead on equal to the absolute value of the strictly larger one. But that's bigger than 1. So this is not a Cauchy sequence. It's a highly non-Cauchy sequence. So this example shows that you can have a type 1 Julia set that is not compact, not compact because you have this non-Cauchy sequence. It has no limit points because it's not even Cauchy. However, Berkovich space is compact, and indeed the sequence now does converge, and in fact it accumulates at the Gauss point. So the sequence of type 1 points that had no limit point in P1 of CK suddenly has a limit point, and it has a unique limit point at the Gauss point. And this is the first time you mess around with the topology of the Berkovich space, it seems very strange that type 1 points could approach a type 2 point. But if you really think about what the topology means, and what does it really mean for in an abstract topological space for a sequence of points to accumulate on another point, it's a completely easy exercise to check that this happens. So, and this sort of illustrates why the compactness of the Berkovich space is a nice fact, because you actually get this crazy non-Cauchy sequence before actually becomes just a very nice thing in this context. All right, that probably killed that example to death and communicated no information at the same time. So let's move on to a little more abstract stuff. Okay, so let's take a polynomial, a rational function of degree at least 2, as always, with Berkovich 2 and Julia sets those notation. Take a connected component of it. Again, we're dealing with a topological space. You can talk about the connected components of this topological space, the Fatou set sitting inside the Berkovich space. So for example, back here, remember the Gauss point was in the Julia set. If you take any single one of these branches extending off of the Gauss point, that was in the Fatou set. So that and that was a connected piece of it. So that if you take one of these single branches, not the whole shaded thing down here, but just one of these single branches extending down here, that would be, for example, a component of the Fatou set in this case. So take a connected component of the Fatou set, take a point in it. It turns out that U is the union of all connected Berkovich affinoids containing that point contained in the Fatou set. So what does that mean? So remember that the Berkovich Fatou set is the set of all points that have a connected Berkovich affinoid neighborhood that is dynamically stable. Dynamically stable, a set U is dynamically stable is when you take the union of all of its forward iterates, you still missed a lot of P1. So this is saying essentially, if you take, so X we know, at this point X we know has some open connected Berkovich affinoid containing it that is dynamically stable. What this is saying is if you take any open Berkovich affinoid containing X that is contained in the Fatou set, that guy will be dynamically stable, essentially. So it's nice that you don't have to worry about, what this is saying is you don't have to worry about dynamically stable. You just need to make sure you're contained in the Fatou set and you're automatically okay. So it's just a geometric property of the Fatou set now. It's not something you have to worry about, some dynamical condition you have to check. It's a technical point though. Less technically, but you need the previous line, I think, to prove this. It turns out that if you take any component and you take the image of it, that's also a connected component of the Fatou set. Now, so I'm saying an equality of sets here. Phi of u is equal to some connected component. One inclusion of that equality of sets is relatively easy. U is a connected Berkovich affinoid. Now remember, Berkovich affinoids are actually connected. I mean, when I was talking about type 1 connected affinoids in the first lecture, I drove this thing home. Yes, they're called connected, but they're not actually connected as topological sets. I don't know if you remember that. But Berkovich connected affinoids are connected. According to a topologist, they are connected. Okay, in fact, they're path connected. So, so the point is, phi of u, phi is continuous also. So phi of u is also going to be some connected set, and the Fatou set's invariant. So phi of u is certainly a connected subset of the Fatou Berkovich set. So what this is saying is, in fact, not just some connected subset; it's a full component. So, so what I'm saying here is that phi not only maps components into components, it actually maps them onto components. And also, if you take the inverse image of a component, you get a disjoint union of full components, each of which maps some degree to 1 onto the original component, and the sum of the degrees is d. So if you have one component mapping onto another, it can't map some of its points, some points 3 to 1 and other points 5 to 1. Like they either all map 5 to 1 or they all map 3 to 1. Again, counting multiplicity. All right, so that's just a technical thing. Oh, but the point is here now, the point is components map to components. So now you can talk about whether a component is maybe fixed or periodic or pre-periodic or wandering. And so let's look at periodic components just for the moment. So, so periodic or including fixed components. So again, same basic data. You have a rational function. Then take a connected component of exact or minimal, whatever you want to call it, minimal period m. So there's a couple of things that might happen. So let's call it an indifferent component if the mapping, so phi to the m maps u onto u by the previous slide. If it maps it into u, then it maps it onto u. So let's suppose it actually maps it 1 to 1. So the smallest possible degree that it can. In that case, we're just going to call that an indifferent component. And another thing that might happen is you might have an attracting periodic point somewhere in u. Of the same period as u itself. And it might even be true that absolutely everything in u ultimately under iteration gets sucked in towards that attracting periodic point. So that's another thing that maybe might happen. I'm saying here it's the same. So one could imagine maybe it's different. So I'm saying these are two things. These look like these are two very special cases which might happen. And they don't even look like they're necessarily mutually exclusive. I mean, it's conceivable maybe that you have this kind of thing happening and the component maps 1 to 1 onto itself. It's certainly conceivable that, yeah, maybe you have a periodic point of a different period than the map itself, like of twice the period or something. Or maybe, something else happened that we haven't mentioned. Well, let me just give away the next slide. No, this is it. These are mutually exclusive, and this is the only thing that can happen. What's about to happen. So this looks like it's some random special cases that might overlap, but no, this is everything, and they do not overlap. But I just gave away the punchline on the next slide. And by the way, just the classical name for a wandering component, you don't normally call it a wandering component. You call it wandering domain because that's a little bit more colorful or something, I guess. But basically now. A domain, of course, is either going to be pre-periodic or not. If it's not, well, it's a wandering domain by definition. If it is pre-periodic, then ultimately it lands on a periodic component, again, by definition. And so the question is maybe one of these things happens. So either you're a wandering domain or ultimately you're periodic. So let's try to understand periodic components and let's try to understand wandering domains. And that's essentially the theme of the rest of the talk, is let's understand those two situations. So Juan Rivera Letelier in his thesis proved like everything, but one of the things he proved was this following classification theorem, which is if you've got a connected component of the two set, exactly one of the following three things happen. Either it's pre-periodic, ultimately landing on an indifferent component, that is to say, one of these components that maps to itself one-to-one, or it's pre-periodic, ultimately landing on an attracting component, that is one that contains a unique attracting periodic point of that exact same period, and everything in the components gets sucked in to that point under iteration, or it's wandering. So in other words, just summarizing the punchline I gave away on the previous slide. So any component certainly either is wandering or ultimately ends up in a periodic component. The periodic components come in exactly two non-overlapping types. They're either indifferent or they have an attracting point. That's it. Yeah, okay. All right, so I've already mentioned good reduction a couple of times. So a little bit just reminding you what it means. You say the map has good reduction. Well, if it fixes the Gauss point and maps the Gauss point to itself with as high multiplicity as it can, or to put it another way that's a little bit easier to understand, when you write it out as a fraction and it's clear denominators, so all your coefficients lie in the ring of integers, and assume you don't have any common factors between f and g, and assume you didn't clear too many denominators, so at least one of the remaining coefficients has absolute value 1. Then the degree of the reduced map is still the degree of the original map. You didn't lose any degree, there was no cancellation. That's what good reduction is. It's rare that that happens, but when it happens, that's nice. And in that case, for the same reason as the first example as I sketched today, which I guess I didn't really actually give the reason for, but it's true that the Julia set turns out to be just the single point the Julia set, just the single point of the Gauss point. And all these side branches that come off, all these open disks, open Berkovich disks coming off, are the Fatu components. And they map to each other in the way as precisely described by the reduced map, which is F bar over G bar. So you can, in other words, you can essentially totally understand the dynamics on Berkovich space by understanding the far simpler question of just dynamics on P1 of the residue field, which is hopefully a much simpler question. Now, by the way, but now, in light of the previous slide, we have this notion of the periodic components could be either attracting or indifferent. Well, it turns out, again, working over the reduced map, working on the residue field, which of the periodic components, that is, which of the periodic residue classes are attracting? Well, they are exactly the ones that have a critical point in them for phi bar. Okay. Now, please note, let me point something out, what I mean by critical point for phi bar. Let's say that K, you have residue characteristic P, positive residue characteristic. So K bar here has characteristic P. In that case, and let's say phi is Z goes to Z to the P. Well, the derivative of Z to the P is 0. Okay, so sort of everything is a critical point. And in that case, indeed, all of these components here are attracting components. They all contain a unique point that sucks everything in. So anyhow, so you get the periodic components that are there are attracting. If they're over the residue field, they have a critical point. Not necessarily over the original field, but over the residue field, if they have a critical point, you get an attracting component. Otherwise, it's indifferent. Of course, if your residue field is big, for instance, if it's characteristic 0 or maybe it's characteristic P, but it's not algebraic over a finite field, then you can also get wandering residue classes. So you might, in which case, you'll get wandering domains. But if your field is like CP, whose residue field is FP bar, then you will not have any wandering domains for a good reduction map. Okay. Meanwhile, here's an example that comes up with polynomials. We've already seen this example a couple of times in various contexts, but let me just say it a bit more generally. So, given a polynomial, it fixes the point at infinity, and that's attracting because its derivative there, so to speak, is 0. All right, now potentially good reduction just means that, well, maybe it's not good reduction, but you can change coordinates so it is of good reduction. So let's assume phi is not in that case. So phi is not just sort of a stupidly simple map. It turns out that the component of the Fatou set containing the fixed point at infinity is definitely not a disk in that if you're not in potentially good reduction. Instead, it's called being of Cantor type, which means the following thing. So I guess I'm going to pretend that Berkovich space is a sphere. Or you can even think of P1 as CK. So I'm going to draw a picture that looks like the Riemann sphere, but really I'm drawing Berkovich space. So there's our Fatou point, fixed point at infinity. What you can do is you can take a certain disk containing infinity, V0, that is the largest possible open disk that is still contained in the Fatou set. So the point is just outside of this disk. There's some Julia points. If I tried to make the disk any bigger, I would intersect the Julia set. Okay, now take the pre-image of that. If you're not of potentially good reduction, as I'm assuming here, it turns out that the pre-image of that, well, it certainly has to contain the point at infinity, and it's actually not too hard to see that it, in fact, contains all of the disk V0. The pre-image does. What's a little less easy to see is that the pre-image has to, it's not going to be a disk, so it has to actually omit a couple of disks down here. So V1 is everything all the way down to here, but it has to omit not just one disk, but I'm drawn it omitting 3 disks, the big disk at the bottom and 2 more disks. It looks like a bandit or something. So 2 disks there. Oh, some of the Ninja Turtles. Oh yeah. All right, and then you can take the pre-image of that, and that turns out that will go inside each of these things and omit more points inside this, and some more disks down here. And so now you get, so V2 is now everything except those disks. And V3 omits even more disks. At each stage, when you take each pre-image, you have to omit more disks inside each end of the thing. So inside each of the disks that you've omitted, you have to omit more than one disk from inside of that. So it starts getting crazy, and it turns out that the full component is just the union of all these things. So in other words, the complement of this component is the intersection of all these disks. So the quadratic example was sort of a simple case of this, where I had the one big disk, and its pre-image was 2 disks, so the pre-image of that was 4 disks, the pre-image of that was 8 disks. This is that, only not quite so simple. And now some of these some of these disks might go to 0, but some of them might not. It could be crazy, it could be a big mess. But in the end, it turns out that the Fatou component containing infinity is the union of all these guys. So the limiting shaded region, everything in that shaded region, well, sort of by definition, ultimately ends up in V0, and then from there it gets sucked off to infinity. So this is an example of a domain of Cantor type. It's an attracting domain. It contains a unique attracting fixed point infinity, which sucks absolutely everything else in. But it is most notably not a disk. So Rivera-Letelier went further in his classification theorem. And he said, for these periodic components, so he's already shown that there are only 2 possibilities, either indifferent or attracting. Well, he goes on to say, if you're indifferent, then in fact, it's not as messy, it can never be as messy as this. If you're an indifferent component, that is, if you map 1-to-1, if your Fatou component maps 1-to-1 onto itself, then U has to be simply a rational open connected affinoid. So for example, a rational open disk, or a rational open disk with finitely many rational closed disks punched out of it. That's the only thing that can happen. And that, of course, has boundary points, each of which are type 2 points, because these are rational open disks. So the boundary points in Berkovich space is just a single type 2 point for each of the disks that you punched out. And phi will permute those. Map that finite set 1-to-1 and onto itself. And those points are all, they have to be in the Julia set, because if they were Fatou, then you wouldn't have the whole Fatou component for U, right? I mean, you can't have, that's supposed to be an entire connected component of the Fatou set. You can't have a boundary point that's in it, but not in it. So anyhow, whatever. You get periodic Julia points on the boundary. And if you're attracting, then either you're a disk or you're one of these guys of Cantor type. And so either you have this horrible thing going on, or you're just simply a disk. And there's no in between for an attracting component. In the case of the open disk, the unique boundary point, remember, for an open disk, its boundary in Berkovich space is not a circle; it's a single point, because you've got it's an open disk is simply a branch off of a type 2 point. So the unique boundary point is just the type 2 point that you branched off of. And in fact, it has to be a repelling periodic point. By the way, the points here only had to be periodic Julia points. Again, there's this funny thing that if your residue field is big enough, then you can have Julia periodic points that are only merely indifferent as opposed to repelling. But in the case of the attracting components, the disk boundary points have to be in fact repelling. Still Julia though, of course. And for the Cantor type, the boundary is guaranteed to be uncountable. And of course, and it's completely contained in the Julia set. In this last case, I mean, I've said what type the boundary points are. In this last case, though, I haven't quite said it yet. They can sort of be anything. The z² plus az example, they were of type 1. In Shah's cubic example, because there was that disk, the closed disk of radius 1 mapped onto itself, it turns out that Gauss point is actually also a boundary point of the resulting Cantor type domain up top. So you can get type 2 points in there. And in his thesis, again, Juan did everything in his thesis. He gave an example, at least over CP, where you have type 4 points. These crazy, if you take these disks, the chains of disks whose empty intersection, he gave an example where there are some type 4 points in the boundary of such a component. It's actually an open question of whether you can get type 3. And that actually turns out to be the same as asking a question of whether you can have a wandering domain that has certain properties, which I won't really get into. But anyway, probably you can. Probably you can get type 3, but no one has been able to prove that yet. I'm not sure how much people have tried, though. All right, but so I've given you examples of disks, both disk attracting and disk in different components among good reduction. Just each of those branches off the Gauss point that's periodic is either an attracting or indifferent component, and it's a disk. And I tried to show you for a polynomial what one of the Cantor type attracting domains look like. The one thing I haven't even attempted to show you yet is an indifferent component that's not a disk. So here's an example of that. And once you get the idea, it's not that complicated. So let's take this map. So it basically looks like 1 over 1, well, it's quadratic. It's a degree 2 rational function. But instead of mod pi here is absolute value less than 1, mod pi, it looks like 1 over 1 minus z. So in particular, please note that, first, please note that the point at infinity is fixed. That's not too hard to see that infinity maps to infinity. And essentially because of this term right here, the pi z squared over z, the multiplier of that point in infinity is pi to the minus 2, which has absolute value bigger than 1. Because when you're up near infinity, basically you get mapped to pi squared times z, which pushes you away from infinity. So infinity is pushing stuff away from it. I'm going to need a fresh sheet here. So get ready to do that. So that's one observation. There's a repelling fixed point in infinity. Meanwhile, the Gauss point is an indifferent fixed point, because if you just simply take this function, or you can look at it this way if it makes you feel better, take it mod pi, you just get 1 over 1 minus z. You don't have good reduction because the degree dropped from 2 down to 1, but you also don't have constant reduction because the degree did not drop all the way to 0. So this is an example of a non-constant, but also not good reduction. Now, it's just easy to check. It's a routine computation to check that if you compose this function with itself 3 times, you get back the identity. And in particular, for example, I put bars here to indicate I'm talking about elements of the residue field. Infinity maps to 0, maps to 1, maps back to infinity under the iteration of this function. Okay, it's also, well, I said that was easy to check. I'll say this is not hard to check, which I think is a level of difficulty harder than easy. So it's not hard to check, although it takes quite a while that all this stuff happens. So let me explain what I'm saying here, because I think this is probably clear as mud what this is saying. So here's a sketch of Berkovich space again. Infinity is up here, 0 is down here, and 1 is over here, and here's the Gauss point. So what I'm saying is here, the first point on the top right there is I'm taking the point corresponding to the disk centered at 0 of radius reciprocal of that of pi. So, and pi had absolute value less than 1, so its reciprocal has absolute value bigger than 1. So take that type 2 point up at the top there. What I'm saying is that maps to this point down here, corresponding to the disk of radius pi, centered at 0. So this guy maps to here. And in fact, it maps with multiplicity 2. But in the sense of yesterday's lecture of how you map points of type 2 to each other and what the degree is. I mean, you can just, it takes 5 minutes to write down all the computations, but you end up getting, it maps to that point with degree 2. And then this point maps to the guy corresponding to the disk centered at 1 of also of radius absolute value of pi. So this guy maps to here with multiplicity 1. And then that guy maps back to here, also with multiplicity 1. So the upshot is that those 3 points form a cycle of, well, type 2 points, but points of period 3. And that cycle is repelling because 2 times 1 times 1 is 2, and 2 is bigger than 1. So it's a repelling 3 cycle. So in other words, all 3 of those points, all 3 of those type 2 points I just sketched in are Julia points. Julia points of period 3, repelling. Meanwhile, it is, you can also check, wow, I called this easy? Okay, this isn't, I shouldn't have called this easy. It takes a while to check, but again, it's straightforward to check that phi maps this crazy open connected aphanoid to itself. So what is this open connected aphanoid? The aphanoid in question I'm describing is that, this is now a drawing more in CK, is the disk, take the disk of, the open disk of radius pi inverse, and punch out of it the open disk of radius pi centered at 0 and the open disk of radius pi centered at 1. So take the sort of a two-hold annulus, take the stuff in between those things. Those disks, of course, are precisely open disks corresponding to these 3 points. Okay, so this annulus, or two-hold annulus, corresponds to everything that's in here. That's this whole region here. Is exactly the scribbled region there, along with, you know, all the stupid little side branches that are heading off of everything off of here. Okay, so that annulus right there, when appropriately Berkovichized, gives you the region I've attempted to sketch in on the Berkovich tree. It's not, again, it's not too bad to check that region maps bijectively onto itself. So every point in that region has exactly 1 preimage in that region, and every point in the region maps into the region. Well, there you go. What I've just, if you believe everything on this slide and you piece it together, what we've shown is that this region here, which I think I just called U, is therefore a connected component of a fixed connected component of the Fatou set. It maps to itself 1-to-1 and onto. You can't put, it is a full component because the only place you could push it bigger, it takes up absolutely everything that's in this region. The only way you could try to push it bigger is to push it out this branch this way, or push it out this branch this way, or push it out this branch that way. All the other branches are already completely contained in you. The only way to make it bigger is to push out this way. But these, we just said, are Julia points. So you can't push off that way without leaving the Fatou set. So this is a full connected component of the Fatou set that maps 1-to-1 and onto itself. So this is an indifferent component. And you can see that, as I promised in the classification theorem, phi does indeed permute the 3 boundary points of it, and they are all Julia. So this is the kind of thing that happens. This is what an indifferent component that's not a disk can look like. Okay, let me switch to, in the remaining 10 minutes or so, let me switch to wandering domains. So the following definition appears to have nothing whatsoever to do with wandering domains. But it's something I need to say. So it's a term that's standard in classical dynamics. You say that a point is recurrent if it is contained in, well, maybe it's not one of its strictly forward iterates, but if you take the closure of the set of all of its strictly forward iterates, you contain the point. So, by the way, please note that's the union over all n bigger than or equal to 1. If I had put a 0 there, then every point would be stupidly recurrent because x would be in the very first set on the side. So, I guess there really should be brackets around the phi to the n of x of it. So what I'm saying is here, what does it mean for a point to be recurrent? Well, a periodic point is certainly recurrent because x, you take some iterative of itself, actually lands on itself, and all future iterates of it land on itself, and that's sort of stupidly recurrent. But it's possible for a non-periodic point to be recurrent as follows. You could have your point x, and some future iterate of it lands kind of close to x. And then some future iterate of it lands really close to x. And then some future iterate of it after a really, really long time lands really close to x, and so on and so forth. So you could have some sequence of future iterates of x approach x in the limit. This is something that might or might not happen. So x is recurrent if that happens. Also, a seemingly unrelated definition, unrelated to the previous line, is if you're talking about a critical point, and I'm thinking type 1 here, you say that the point is wild as a critical point if its multiplicity is divisible by the residue characteristic. So of course this can only happen if the residue characteristic is positive, but the idea is, let's say work over QP or something where the residue characteristic is P, then 0 maps to itself wildly under the map z goes to z to the P, because P is divisible by P. All right, so this was my thesis, given I proved it for the p-adics, I guess, but essentially the same proof works in this situation. So take any locally compact non-archimedean field and take its completion of its algebraic closure. Please note, since I said it's a locally compact non-archimedean field, for the original field K had to have, since it was locally compact, it had to have finite residue field. And if any finite field has positive characteristic. So K had to have positive characteristic, and therefore CK, its algebraic closure completed, also has that same positive characteristic. But K itself, of course, may be characteristic 0. So take a rational function. I'm going to talk about the type 1 Julia set of it, but the Berkovich-Fatou set of it, for reasons that will hopefully become clear. Suppose that, well, there's two possibilities. Either the characteristic K is actually also that positive number P, or it was actually characteristic 0. So characteristic K is P, that's like the function field case, and characteristic 0, that's like the p-adic field case. So if the characteristic is P, you have to assume that there are no wild critical points in the type 1 Julia set. And if the characteristic is 0, you can assume the weaker condition. You are allowed now to have wild critical points, but you're not allowed to have wild critical points that are recurrent in the Julia set. This is just a technical assumption that you need. I needed it anyhow to make the proof. Maybe you don't need it to make the proof go through. Then the conclusion is there's no wandering domains in the Berkovich-Fatou set. Given time constraints, I think I'll skip through the proof, but it basically hinges on a certain power series lemma. So yeah, I'm running short on time. I don't want to bore you with the proof. It was my thesis, so I like to plug it. But you don't want to see that. All right. Anyhow, so there's no wandering domains. Well, except that there can be wandering domains. So when I first got the result, I mean, the hope was sort of, I had to assume these technical hypotheses. So there's sort of two technical hypotheses here. One is, on the one hand, the field, please note, phi is actually defined over a locally compact field. We're working over CK, which is not locally compact, but the function itself was defined over a locally compact subfield. So that was one assumption. And the other technical assumption was this: either no wild critical points or no wild recurrent critical points in the Julia set. And so, the hope was these are just technical assumptions that I needed to make the proof work, and we really shouldn't need those. Well, back at the time, that was when anyone who was doing this, which was basically me and Juan, were working on p-adics, and we weren't looking at other non-Archimedean fields. So if you work over other non-Archimedean fields, you can get wandering domains quite easily. So for example, if the residue field is not algebraic over a finite field. So this will happen if the residue field has characteristic 0, for example, but it will also happen, it could be characteristic P, but just be a very large characteristic P field that's not algebraic over a finite field. So if the residue field is not algebraic over a finite field, as soon as your map has a type 2 Julia periodic point, so it has to be Julia, so it's either repelling or one of these wacky and different ones, then you get wandering domains, just instantly. And they're said to be in the basin of attraction of the point. So the idea is here, well, what's going on? So let's say it's a type 2 fixed point. So somewhere in Berkovich space, you have some type 2 fixed point zeta, so that maps to itself, and it's Julia. Well, it turns out most of the residue classes coming off of it, you can show, or a lot of them anyhow, are completely Fatou, completely controlled. Some of them will be really bad, but most of them will be pretty nice. And the thing is, you've got so many residue classes because you're not algebraic over a finite. Because you're not algebraic over a finite field, you have a lot of residue classes. And in particular, it's not too hard to show that some of those residue classes will be wandering. I mean, this is just a fact. If you take a field k, little k, that is not algebraic over a finite field, and you do dynamics of any polynomial, any rational function you want on it, you'll get wandering points. So therefore, those will correspond to wandering residue classes off of this. And you can show that not too many of them are actually bad. So you just get wandering domains automatically. But they're all set of control. They're all in this. By the way, the reason it's called in the basin of attraction is if you follow such a wandering domain around, take a point in such a wandering domain and follow its iterations, then in the Berkovich topology, the limit of that point is actually the point zeta. I mean, it doesn't seem to actually be getting closer to it, but that's again because it's hard to picture what the topology on this crazy infinite space is. So, but it is actually topologically approaching it. So that's why it's called being in the basin of attraction. And in the topology, it approaches zeta. So you can get wandering domains this way, but they're sort of stupid. Or they're not too evil. So then there's a couple of results I want to tell you about. This is a more recent result of mine that if you assume the case that the residue characteristic is 0, and again I need to make an assumption about the field of definition, not that it's compact this time, but at least that it's discretely valued. So I can't, for the field of definition of phi. In that case, well, you can have wandering domains because you're going to have these wandering domains in the basin of attraction of a point like this, but that's it. The only wandering domains you can get in this situation are these basin of attraction wandering domains, the stupid ones that you get anytime you have a type 2 periodic point over with such a residue field. I don't want to get into the proof of that. Just recently, I haven't even met this guy yet, but I think this was his PhD thesis. He posted this to the archive this past fall. I believe he's a student of Jan Kiwi at Santiago. Anyhow, so Eugenio Trucco proved that if you work in this field of Puiseux series over the algebraic closure of Q, and his paper is technical in like 30 pages, I think the proof probably goes through for any CK who's a residue characteristic 0, but I can't promise that. But certainly for the Puiseux series field over in characteristic 0, then same conclusion. There's no wandering domains besides those that are unattractive. So the key thing here is he does not need to assume the discretely valued assumption for the field of definition. And this condition really should not be required. Again, it was a technical condition I needed to assume. Trucco managed to find a way around that. But on the other hand, he only proves it for polynomials. And his proof is definitely polynomial specific. And then let me just close with a couple of closing comments. So it turns out, though, there's the other, well, you can also, even over CP, you can have wandering domains. I suspect you can't over QP bar, but over the CP, the completion of QP bar, you can have wandering domains. And more generally, as soon as your residue characteristic is P, you can write down, you can find parameter values of A sitting inside of CK such that this specific polynomial has a wandering domain that's not one of these basin of attraction wandering domains. And this is a really nasty construction, but well, I also think it's kind of cute. And if you're interested in that, you can see Project 4 from my gang. But by the way, again, all of the things I was just talking about, all of these various examples of wandering domains, I was breaking my original theorem by removing the assumption that the field of definition was locally compact. So all the wandering domains I've just been telling you about happened for where the field of definition of phi was not locally compact. So what if you reinstate that? Declare that the field of definition of phi has to be locally compact. Can you break it? Well, you can certainly break the hypotheses. So the other hypotheses were these no wild recurrent critical points, or in the case of residue characteristic 0, in the case of the positive characteristic, no wild critical points at all, they're Julia. Well, it's really easy, once you think about it, to get a wild critical point in the Julia set. This map here, for example, has a wild critical point at 0. You can see that because of the z to the p and no lower power terms until you get to 1. So there's a wild critical point at 0. And it's not too hard to check that that maps to 1, and that 1 is a repelling fixed point. So 1 being repelling fixed is Julia, 0 being a preimage is also Julia. So you have a wild Julia critical point. just easily rig that up. Does it have wandering domains though? I have no idea. If you can figure out whether this map has wandering domains, that would be good to know. For wild recurrent Julia critical points, again, it was Juan who proved, yes, you can get wild recurrent Julia critical points even over QP. Very technical construction, again, C Project 4. But in both cases, we don't know whether there can be wandering domains. So if you can figure that out, please let me know. I'll stop there. Thanks. Oh, sorry, yeah. So he does, he takes this, disk containing infinity, the kind of thing with this diagram. I mean, if you thought this diagram was ugly, Trucco must have spent basically 3 years just staring at this diagram, this kind of thing. Because he starts with he essentially starts with that disk V0 and looks at the pre-image and looks at the pre-image, and he keeps this insanely careful bookkeeping of what the radii of all the disks are that appear along the way, and does all this stuff about proving what can happen with these